Okay, I think we'll go ahead and get started. This is Dave Castor with EasyPower. It's good morning or good afternoon, as the case may be, and thanks for joining us. We're going to talk for a little bit here today about power flow, kind of continue the discussion that we had 2-3 weeks ago, and just point out some additional features and capabilities and of EasyPower and how the power flow solution works and what it can do for you, and just to kind of get a better understanding of power flow in AC power systems, because it can get a little confusing. So I have a few slides here just to kind of remind me what to talk about, and then we'll jump into some examples. So we're going to talk about what it is in the system, your power system that you model, that controls the real power, the kW, and what controls the reactive power in VARs. Last time we talked a little bit about the generator settings related to power flow. We're going to kind of review that and talk about that in a little more detail and take a look at some examples. We'll also look at having generators and utility in parallel, and what your typical settings might be for that power flow in that situation. And then we'll look at what happens if I have multiple utility sources tied into my system, and how that can lead to some surprising results sometimes. And then we'll discuss a little bit about how to scale the loads and the motor loads in your model to get a realistic power flow, because I think we discussed last time, if you just use your connected load, you're not going to get normally a realistic power flow. You're going to have way too much load reflected in your system. And so when we run power flow, this is not the same as doing our load calcs for sizing cables for the National Electrical Code or things like that. This is strictly an attempt to simulate the actual conditions in your power system. And normally we're worried about specific conditions like peak demand periods and maybe minimum demand, that kind of thing. But we need to scale the loads to simulate those. And we're going to talk a little bit about load tap changers and how EasyPower has the ability to model the effect of the load tap changer, so it'll automatically select the appropriate tap to maintain whatever voltage set point you ask within the limits of what is possible. And then if you do any work with electric utility systems, distribution systems, you're familiar with the step type voltage regulators that are used to, similar to a load tap changer, to maintain voltage within a specific range. And we'll talk a little bit, we don't have a specific model for that in EasyPower, but we can model that as a transformer, and we'll talk about how to do that briefly. And then finally, we're going to talk about troubleshooting. You will experience at times the issue that the power flow solution will not converge. You'll get error messages on that, and then have to figure out what's going on. We'll talk about the most common things that can cause that to occur, and how you might go about kind of troubleshooting that and coming up with a solution. So then we'll probably have some time for questions at the end. So so let's talk about real power, the kW, that the power flow is computing. So we know that in a real system that the energy in the system has to be conserved. And the same is true in our power system. So basically the way the power model works is the power into your system must equal the power that's consumed plus the losses, but minus any power that's exported out of your system. And that can occur if you have two utility sources. You can have power going around in one side and going out the other, and we'll take a look at an example of that. But everything has to balance out. And basically the power consumed is determined by your loads and the scaling factors that are being applied to the loads and the type of loads. So we went through this last time, but just remember that the reason this gets complicated is because if I look at any individual load, to some extent, the power consumed by the load depends on the voltage, or it can, depending on the type of load. And almost all loads are somewhat voltage dependent, some more than others. But the voltage that the load sees depends on the load, because you have voltage drops in the system, like across your transformers and in your cables. So there two things are interdependent. The only way to solve that is to iterate, and until everything balances within the accuracy that you specify. But basically, the program's going to iterate until everything balances out. All right, just as a review, in each power system, you must have at least one swing source, sometimes called a slack source. So that is a source that can produce as much power as necessary to solve the power flow solution, or it could absorb as much power as necessary. So it's kind of the infinite source and sink for the power flow. So if you do not have at least one swing source, you're going to get an error message from EasyPower. So as we'll see, when we look at generators, if your generator is tied to the utility, you're probably going to want to make the generator something other than a swing source. But if you have a standby generator and you're trying to model that for power flow, then you need to set that generator as a swing source, because when it's running, it's going to be isolated from the grid. So that has to be a swing source to run power flow. Now, the thing that can be a little bit confusing to people when they're dealing with AC power systems is that the voltage is not the primary factor in determining the real power flowing in the system, as opposed to a DC system where it's all dependent on the voltage. In AC systems, that's not the case, because we have reactive power, we have phase angle differences. So the main thing that determines the kW is whatever you specify for your loads, and the losses have to be accounted for. So voltage is not the primary factor. So I'm just going to jump over here to not that case, but this model here. We'll just take a quick look. We'll be focusing up here. So I've got a utility source here. I've got a couple generators. There's another generator hiding down here somewhere. So in order to run power flow, we go into power flow focus. If you had any missing data, you'd get an error message right there. Sure, you're probably familiar with those if you've done much modeling. And now, unlike short circuit, the power flow solution is I have to solve the entire network. So I don't have the option of running power flow on one bus or one generator. So I just go up here to solve, and I get my solution. We looked at this in our previous session. So the thing to keep in mind is that this 104 megawatts, that's determined by the loads in my system and the losses, and I have generation here as well. So everything has to balance out. So that's really what determines the kW, or the megawatts, not the voltage. The voltage is a secondary effect. So if I were to, we'll come back and talk about this in a minute, but if I were to go into this generator now as temporary data, we'll see this generator is set in PV mode to generate a constant 26.5 megawatts. If I reduce this, let's say I change it from 26.5 to 20. So I've taken 6.5 megawatts out of my generation. So when I say okay, it's going to rerun the power flow. Well, that 6.5 megawatts has to be made up from somewhere, right? So because this is scheduled at 40, that's going to stay 40. So it's going to come from basically my swing source, which is the utility. So I've reduced that from 6.5 to 20. So this is going to go up roughly 6.5. So you can see now it went from 104 to 111 and some change. Now it's not going to balance out exactly, because as I take more power from here, I have the losses in the system change a little bit, and that has to be made up as well. So that will have some impact, but basically it's a one-for-one exchange. If I take power out here, it's going to have to be made up, and it's going to get made up from here. This is my swing source. This stays 40 because that's what I told it, right? 40 megawatts. So that's not going to change as long as I'm in the PV mode. All right, so just remember that the kilowatts or megawatts that show up are really based on the loads that you defined. If I go down and look at a motor loader, this is computed at 7,000 horsepower motor when EasyPower applied the efficiency and power factor that I specified in the motor data. Came up with 6871 kVA. That's the load. That's what the program is going to use, times this scaling factor, which was defined in the database. I can change it here, but that's how it determines the load. It uses the load type to determine how the load responds to changes in voltage. So the default is constant kVA, which means these numbers are not ever going to change as the voltage changes. That's not totally accurate, but it's the most conservative approach. If I were to change the load type, then these values would change as the voltage changes in a slightly different way. So you can kind of play around with this to see the impact that it makes. Typically, the motor is going to be conservatively kind of like a constant current or kW plus some reactive current model, but we default to the constant kVA because that's what most people use, and it's the most conservative. So what happens on a constant kVA load, as the voltage goes down, at the motor goes down, it's going to increase the current to produce a constant kVA. So the sum total of all these loads and times their scaling factors is what determines the kW in the system. Okay. So we'll contrast that now and talk about reactive power. Let me get my PowerPoint back up. So when we talk about reactive power, the system has to balance out. It's the same as the real power. So when it runs the power flow, when we do power flow, we talk about VARs or megavars or kilovars. So the VARs we call reactive power, imaginary power. It's not real power. It's not real energy. It's reflection of the phase angle difference between the voltage and the current, right? The power factor. But you can treat them as if it was a power flow, and that helps us to understand what's happening in the power system. And like the kW, these must balance out. All right. And what the VAR flow is most closely related to is your system voltages. So if I add a capacitor on a bus, I have a huge number of VARs flowing out of the capacitor into my system. That's going to raise the voltage. So if you think about a system where I have a constant power requirement, kW requirement, if I change the voltage, I need the VAR flow to account for the voltage drops I'm going to see in the system. Because remember, the real power is not really changing. So what changes is the VAR flow. And when you have things like a generator tied to a grid, or you have two grid sources, very small changes in voltage can make huge differences in your VAR flow and reactive power. So we'll see when we do the two utility sources, if these are tied to a common bus, if you have two sources tied to a common bus somewhere, those two voltages are the same at that bus. That has to be the same voltage by definition because they're tied together. So to equalize that, whatever the voltage is at each source, there's a VAR flow that happens to balance, create voltage drop through the impedances of the system to equalize those two voltages. And we'll take a look at how that works in a minute. All right, so let's go back and take a look at our model again here. So if we take a look at our power flow solution here, we have 111 megawatts and 38.774 megavars, and the arrow tells me which direction it's going. Now the convention is these are lagging VARs flowing into my system, right? So that requirement, everything has to balance out, right? Let me go to my text report here. If I run a system summary report, this is what it's going to look like. Here's my megawatts. I have 183 total generation. Here's my load, and here are my losses. Those have to balance out, and here's the check, 0. So that balances out. Same with the VARs. They have to balance out, right? So I have 102 VARs being created, flowing in. I have 95.7 megavars of load. I have shunt load here these could be capacitors in the system, and then I have losses. VAR losses are typically much higher than the real power losses. So this is not really a loss that you have to pay for in your system directly, but it's VARs that are getting consumed across inductances, primarily like transformers and motors. Okay, so this is what the program is doing. It's iterating until it gets this check down to 0. So let me turn that off so it's not going to bother me. So what happens? Well, let's take a look at these voltages here. What determines, why is this voltage 1 per unit? Well, because it's a source, and we've told the program that it's 1 per unit right here. That's by definition. So the program's always going to make this come out so that voltage stays 1 per unit. This is your source utility voltage. So if I don't change anything else and the utility voltage goes up, say it goes up to 1.02 per unit, what's going to happen is I'm going to have more VAR flow here. So this made a sizable increase because I've got additional voltage here, so that's going to create more VAR flow down into my system. And that VAR flow gets used up in the inductances of my system, like across the transformers and my cables and anything else that has inductance in it. So the real power doesn't change very much. It changed a little bit because the current went up. If I go to my power flow options, I can change what I display on the one line for the branch flows. If I want to see amps, I can do that. Okay. So here's 605 amps. If I change this back to 1 per unit, my amps go down, right? If my amps go down, then my losses in my system go down, my I squared R losses. So that affects this K, the megawatt, the real power a little bit, but it's a secondary effect, right? Now, if I change this back to 1.02, you'll see my amps go back up again. So it's really the voltage difference that's driving this, and that's because of the VAR flow here. And so when you start playing around with changing your voltage, you're going to want to do it in really small steps because 1% voltage change is fairly significant in the system. If you start changing it by 10%, you're going to run into issues. Now, in database, I can tell the source which voltage I'm trying to regulate. So it's going to default to the bus it's connected to, but you could pick a different bus here. And this is the swing source, right? So by default, utility sources are always modeled as swing sources. You can change that, but that would be an unusual situation. Okay, so the other place the voltage is set is at the generator bus here. If I go look at my generator data, when I'm in PV mode, which is regulating voltage, I tell it I want 20 megawatts, but I want to regulate the voltage at this bus, GSU3, I want to regulate that to 1.03. So the way the generator does that is by changing, this is analogous to the actual voltage regulator in the generator. It's going to increase the excitation until to maintain this 1.03 per unit voltage. When that happens, you have additional VARs that flow out of the generator. It's overexcited, so you have VARs that flow out. If I change this, if I reduce this, the megawatts are going to stay the same. But these VARs are going to go down pretty significantly here. Okay. Now, if we went up here and looked, we'd see these VARs had to go up, right? Everything has to balance out. My loads still require basically the same amount of VARs. This generator can provide some additional VARs, but there's quite a bit of impedance between these two generators. So the bulk of the difference is going to be made up by my swing source. So again, I'm not changing the real power. I'm changing the VARs are closely related to the voltage here. Okay. So sometimes people talk about circulating currents in power systems. What they're typically talking about is VAR flow that's occurring because the voltages, when you tie the system together at some point, you have to have VAR flow across all your impedances to balance out the voltages. If you have a different voltage at each end, then you need that VAR flow because where you tie them together, those voltages have to be the same. So utilities run into this when they try to tie feeders together out of them, 10 miles from each substation, they tie them together. You can have a lot of VAR flow there because even though the voltages are roughly the same and in sync, the voltage magnitude differences create potentially a lot of VAR flow. All right, so while we're looking at the generator, let's kind of review what we're changing here when we change these values. So remember, when I'm in Power Flow and I double click on this generator, this is temporary data. So when I go back to database, I'll have a choice whether or not I want to save these. So a lot of these things we can change while I'm in Power Flow. Some of the things we would have to go back to database, but this is pretty much what you would see in database. So the default's going to be PV, which stands for constant power and a constant voltage. So basically, I'm telling it I'm going to run at 20 megawatts, and I'm setting a desired voltage, and it's going to be at this particular bus. So what's going to happen is the Power Flow program is going to adjust the voltages, adjust the VAR flow to maintain this voltage. So over here we have limits for the VAR flow. We have minus and positive values. So these are the maximums you can set in megavars. Now in the real world, obviously my machine here is not capable of producing this many VARs, right? The generator has a certain MVA rating and it has a capability curve. So there's going to be limits to the amount of VARs it can produce because the VARs relate to current. So ideally, you would set this for the based on your actual generator capability curve. The reason we default to these extreme values is because you can run into problems with the program not converging if during one of the iterations it hits these limits. So you're best to leave these set really wide, and then you're going to need to look at the result to see what the generator is actually producing in this solution to make sure it's possible to achieve that in the real world, right? So that's the PV, right? And this is analogous to a normal operating generator because this megawatts, what determines the megawatts, right? It's not the voltage, we already said that. This is determined by the prime mover. If I have a steam turbine, this is determined by the steam pressure, steam flow, which is determined by the control valves on the turbine, right? This is the amount of energy that you put in. So I can hold that constant while the voltage varies. And while other things are happening in the power system, that can stay relatively constant. So this is fairly realistic in terms of a real world operation. So swing, we know what that means. That means we're going to let it swing between whatever extremes it needs to balance out the power flow solution. If I go back to PQG, I'm scheduling the megawatts just like I did in the PV, right? I'm going to say I want 20 megawatts. The only difference is I'm going to tell it exactly how many megavars I want. So this is pretty much analogous to being in power factor control mode, if you're familiar with that, or VAR control on a voltage regulator. So now when this runs, this is going to stay 20 megawatts and 18 megavars. You can see my voltage is starting to creep up here. So regardless of what happens to this voltage, this is going to stay the same. So why would you want to do that? Well, if we look at operating in parallel with the utility, we'll take a look at that in a minute. Sometimes operating in the voltage control mode is not really going to work for you. So this is a more realistic situation where I have a small cogen generator tied directly to the grid. Okay. All right, so just remember that you need to select the right conditions here, operating conditions, before you run your power flow for the generator. And these settings only affect power flow. They don't affect short circuit calcs or arc flash or anything else. This is only for power flow. So normally the default's going to be this PV. You might switch to PQG. If the generator is running isolated, it'll need to be a swing source. Okay. So let me jump back over here. So we've talked about these a little bit. One thing wanted to point out, when I have generators on a common bus, if I'm running PV, they're both going to have the same voltage set point. Otherwise, the program's going to change it for you. If you think about it, if both the generators are tied to a common bus, they pretty much have to have the same voltage. There's no way there's no voltage drop between the two that I can use to change, have one have a different voltage than the other, basically. Okay. All right. So we're going to talk a little bit more about generators in parallel with the grid. We've already said that normally the utility is going to be the swing source. And in the real world, a small generator tied to a big grid, which is like a huge generator, may not be able to regulate the voltage, right? It's like, you know, you're having a tug of war with a 2-year-old and a football team. You kind of know who's going to win that one. So running those in PV can create some problems. We'll look at an example. Now, in the real world, you may run that generator in PV, but have actually a maximum excitation limit. And so you'll need to make sure your solution is within that range. And as we said, you probably want to maintain those high values of min and max megavars in the generator settings to avoid divergence problems in power flow. Okay, so I've got another simple little model here that I put together, and go back to database. And we'll simplify it here a little bit by deactivating these guys right now. We're just going to focus on one generator in parallel with the grid. Okay. So remember, you can use this deactivate tool in EasyPower to basically turn these off, but not take them out of the database. So these will be ignored in any analysis that we do, and they're shown kind of grayed out here. That's the deactivate and activate. All right, so I've got a utility source, and I have a small 5 MVA generator tied together on a 13.8, and here's my simple load down here, 15 megawatts, 10 megavars. Okay. So if I go to Power Flow and solve this, you'll see I have 1 per unit voltage here. I have my 15 megawatts and 10 megavars because I have a constant MVA load, and so that's always going to be that. My generator, I have 4 megawatts, but I have 10 point something megavars here. So I only have 10 megavars of load. So where are the rest of these megavars going? Well, they're going back out. So why did that happen? Why is this producing so many VARs? It's because of what I told it. It's my fault. If I look at my generator data, it's PV, which means it's going to try to control the voltage. I'm saying at the main switchgear bus, I need 1 per unit. And I want to schedule it for 4 megawatts. So that's exactly what it gave me. But unfortunately, on a 5 MVA machine, there's no way I can operate like this, right? 10 megavars is exceeding my rating. So if in Power Flow, we can use our smart breaker feature. So if I double click on this breaker, it's going to open. And now you can see all the power is being supplied by the grid, right? So I have my load here is being supplied, but look at my voltage. It's 96.3%. So in this condition, I have my 1 per unit here, which is what I told EasyPower I was going to have. But I have voltage drop across the transformer that's resulting in this low voltage. By the way, you can look, we have an option here to display the voltage drop. In this case, 3.65% across the transformer. So when I put the generator on, it's saying, hey, I gotta get this voltage up to 1 per unit because that's what you told me you wanted. The only way I can do that is to overexcite the generator and pump a lot of VARs in. So that's what it does. And that's where I get the 10 megavars. It's because of my requirement to maintain this 1 per unit voltage. So I'm saying, well, maybe I can live with something less than 1 per unit, right? So I can go in here and reduce this voltage set point. Let's take it down to 0.98. Now when I rerun this, we're going to see these VARs drop and the voltage will come down. So now I'm down. I'm still probably overloading the machine, but at least you can see the impact that the voltage setting has on the VARs, right? Again, my load hasn't changed. The only thing I'm changing is how I'm supplying it, and the voltage drops along the way. So let's say we have a situation I'll leave it at 0.98. So we'll say we're going to operate that way. So what happens now that when the utility's having a bad day and their voltage goes down, it's not 1 per unit anymore. It's, the utility's allowed a spread and an acceptable range of voltage that they can deliver to you, and it's plus or minus 5%, right? That's at any time they can run from 0.95 to 1.05 indefinitely, and they can change it whenever they want and still be within the ANSI acceptable voltage range. So let's say something's going on and their voltage goes down to 0.97. So now what happens is this VAR requirement goes way up, right? Because I have 0.97 here, so I have even more voltage drop across the transformer. The only way I can maintain this voltage is to pump more VARs in from the generator. So now you can see I'm pushing, I still have 11 megawatts coming in, but I have 3.77 megavars going back out into the system. So less the VAR loss in the transformer, I've got about 3.3 megavars going back into the utility system, which they probably don't really mind too much for the most part if it's a peak load situation. But you might care because your generator really can't operate like this. Just a point of terminology. Sometimes people throw the wrong names around for this, but just remember when the generator is producing VARs, it's operating in a lagging mode. It's overexcited or lagging when it's producing VARs. When the generator is absorbing VARs, then it's leading. And there are limitations on both ends, and your generator capability curve will tell you that. So if I were to reduce this voltage significantly, then it's going to reduce. Let me increase this here. Then it'll probably diverge. There we go. So now I actually have VARs going into the generator. This is underexcited. And this is, the generator is operating at a leading power factor. If you drew out the vectors, phasors for the current and the voltage, this would be a leading power factor condition. Okay. So the main point there is that this generator cannot maintain this voltage by itself, right? If this voltage goes down and I'm trying to maintain this voltage, this generator is it's going to go to fully excited and still not going to be able to produce enough VARs to maintain this voltage. So at some point, you're not going to be able to operate in constant voltage mode. You're going to have to switch to some kind of VAR control or power factor control. So now I just set it to run at a certain VAR output, then the swing source will always make up the difference. All right, so if you think about it, if you have a cogeneration system at your plant, what do you get paid for? You get paid for megawatts, right? You don't really get paid for VARs. So you would like to operate really with not very many VARs. You probably want some just for stability. You don't really like to go underexcited. You're going to want to reduce that as much as possible. Now the utility may not like that because they end up providing less megawatts and more VARs, and they don't get paid for VARs either. So other than your power factor penalties. So there's a little bit of negotiations that goes on there and back and forth about how you're going to operate that generator when you have a cogen system. So just keep in mind, you have to be careful when you're operating these in PV when you're in parallel with a big grid. All right, let's take a quick look at a different situation when I have two utility sources tied together. Let me go back to database. Whoops. Let me activate. So now I have two identical utility sources. So when I run my power flow, I have identical power flow from each source. These are both swing sources. So my generator is still doing its thing, trying to hold this voltage up here. But now I have split the utility load between two sources. So these transformers are identical, so basically everything is divided up equally. Now if I were to change this transformer size or impedance, then the contributions would not be equal. So we talked about the kW not being a function of the voltage. So the VAR flow is going to be set by the voltage. So if I were to come into this source and say that it's going to be 1.01 and this is 1.0, so now I get much more VAR flow coming from the higher voltage, and I take less, a little bit less from the generator. Okay. So now I'm balancing this out because I have, obviously where these connect to this bus, those two voltages have to be the same. So I have more voltage drop across this transformer than I do this transformer. That's where I'm asking for 2% more voltage here than here, and so here's how it happens right here across this transformer because of the additional VAR flow. Okay, so the VAR flow is totally determined, almost totally determined by the voltage. But what about the power flow? I have two swing sources. How does we determine how the power requirements get split between the two sources if everything else is equal? Well, we have what we call the control angle, and this is the phase angle between the two voltage sources. I call it the power angle maybe. And so if in an AC system, what happens when I have a turbine generator and I increase the steam to the turbine? I put more kW into the turbine. The generator tries to speed up, but there's a restraining torque because I'm in synchronism with the system, so it'll accelerate a little, move ahead a little bit, and the angle of the generator to the power system will increase. That's the control angle. And when I have a control angle increase, I'm exporting more power. So a very small angle can make quite a bit of difference here. Let's put this is in degrees. Okay, I'm going to put a 1 degree angle on this utility one. This one will be 0. We're going to rerun this. So now you can see this went up to 8 megawatts and this went down to 2.7 because this has a slightly advanced control angle. I can go higher. Now at 2 degrees, basically I have almost no power coming down this way. So what happens if I go higher, 3 degrees? Well, now I have 13 megawatts, but I still only have this amount of load, and I still have 4 megawatts coming from here. So where's the extra power going? Well, it's going back out, right? This is a swing source, so the power can go either direction. So this can happen in the real world. If you tie two utility sources together and use your system as the tie, the power can go right around. And this creates all kinds of headaches for everybody. So this is why you don't really like to do this. So if you're a utility and you tie two substations together, you can have reactive power flow, a real power flow around your system like this. So this is all a function of this angle here. If I change this back to 0, then that's going to balance out. And now we're back to identical VAR flows. All right, so you can have as many swing sources as you want, and so the thing is, the program has no way of determining what that angle is. That's data that you have to tell it. So you have to know if there's a phase angle difference between the two sources. So that's, that's just kind of a special case, and you would have to, if you're a utility, you might have some information about that, or you could do some kind of what-if scenarios. Typically what you might be trying to do is simulate a condition that you observed in the field. If you see power flowing around like that, you can experiment with different control angles to figure out what was really going on in the system. Okay. So I'm going to jump back over. We're going to talk a little bit about modeling, scaling your loads, just to give you some ideas about how to do that and some shortcuts maybe that you might not be aware of. So let me jump back over here to my PowerPoint. And we talked about this. Multiple swing sources. I didn't look at this slide. We've already talked about all these things. Again, the last thing I was mentioning, that EasyPower cannot tell you what the control angle is. That's an input to the program. So that's something you have to tell it. The control angle, if there is one, between the two sources. All right, let's talk a little bit about the nuts and bolts of scaling the loads. As we've said, if you just run power flow on your model using the connected load, everything running at 100%, it's probably not going to tell you all that much because your system's not going to run in that condition. So you need to have some actual load data. And then scale the loads to match the data that you have. So ultimately you should be able to get utility data for your peak demands on your power bills. And from that, you know what the total is, and you can scale the loads. So you come up with an answer at the utility interface that matches your power bill. Of course, the problem is you don't know exactly how the loads should be scaled. Individual loads should be scaled. So you're going to try to get metering data as far down into the system as you can, and then you just have to make approximations and do the best you can. One of the ways we can speed this up in EasyPower is I can select any part of my system, drag a box around it or selection rectangle, and I can automatically adjust the scaling factors for anything in that selection group all at one time. Now, unfortunately, we don't have that capability for adjusting the power factor. So if you're changing the power factor for a motor, that has to be done on a per motor basis or via some kind of copy and paste. And if you're modeling different loading conditions, you're going to want to use the scenario manager. All right, so let's take a quick look at the model. Let me go back to the other guy that has some more loads in there. All right, so just as an example, go back to database. So we've looked at this before, but here is my power flow tab for the motor. There's a scaling factor here. So it's going to take this kVA times this scaling factor, and that's what the program uses. Doesn't care about the demand factor or any of that. It's going to use the kVA. This kVA is computed from the power factor and efficiency and the horsepower. If you put a full load amps in here, it's just take the full load amps times the voltage, and that's the kVA. All right. So when I'm in Power Flow, I can adjust that scaling factor for any motor or any load as temporary data. But I can also do it as a group. Let me run the Power Flow here real quick. So if I look at this, and I see, this is turned red because the voltage is low, 0.923. And it says, well, 1800 amps or 1780 amps. If let's say I had some kind of a meter here that tells me the peak current's only, the max it's ever been is 1200 amps or some lower value. Well, I can scale my loads, right? So the way I can do that is I just select what I want to scale, and I have a button here that says scaling factor. So for those loads in the MCCs, right now they're all at 100%. So I can change all those as a group. Let's make them 70%. And the panel, I don't think there's a panel. Maybe there's a panel in there somewhere. So it's telling me it's going to change those. So now it's going to rerun. So now I'm down to my 1200 amps. My voltage is still a little low, but that's a way you can quickly, so whatever you pick here, you can go to scaling and change the scaling factors automatically, okay? As a group. That's going to speed up your process. So wherever you have load data, you're going to want to scale the loads downstream of that to match that data and then kind of work your way up. So the farther down in the system you have the load data, the more accurate your model is going to be. Okay. All right, so I'm running out of time. I want to talk about, briefly talk about load tap changers. Let me go back to my simple model here. Now, if I get rid of these sources, we saw that we have pretty significant voltage drop across this transformer. Now, if in the real world this transformer has a load tap changer, we can model the effect of that in EasyPower. So if we go back to database, there's a tab called LTC, which is load tap changer. The default's going to be none. I tell it if I want on which winding that load tap changer is on. The from is going to be, in this case, the 115, and the to is the 13.8. So typically it's going to be on the low side on a transformer like this. I'm going to say 2. The step size is the voltage difference of each tap from one tap to the other. Typically it's plus or minus 10%, and there's 16 plus or minus 16 taps on each side, so it works out to 0.625. Here's the min and the max. This, again, is just kind of analogous to the big mega VAR range we set on the generator. We want to keep this really wide so the program doesn't stumble on that if it runs outside of its range. And here's my set point. This is just like the set point we set for the generators. Okay. And I probably, okay, so that should be good. So now when I go back to Power Flow, I'm going to rerun this, and now I have 1.07. This is telling me that's because it's increased the tap. So if my nominal was 13.8, it's up to 14.418. So EasyPower adjusts the tap until it gets the voltage up here to what I told it I wanted it to be. So this will tell you what tap you need to be on, or where the LTC is going to end up for this particular loading condition. Okay, so that's a way you can simulate the operation of the LTC. But remember, this is a steady state solution. So if I have some kind of impact loading, like a motor starting, I need to block the LTC because the LTC is slow. it's not going to respond during motor starting, or it's not going to respond quick enough to help you. So if I go into my temporary motor data, or transformer data, we can block the LTC. Okay. You can also specify a tap here, but typically what you're going to want to do if you're doing some kind of impact loading, you're going to want to block the LTC action. And that'll lock that in, and you can see what the impact would be. But you can turn that on or off here as temporary data. Now, if you have a utility system with step-type voltage regulators, which are basically auto transformers with a load tap changer, you can model those as just a two-winding transformer with an LTC, just a 1-to-1 voltage ratio with an LTC and very low impedance. We don't have an explicit auto transformer model, but you can model it as a two-winding transformer. And then you can put in the LTC and it'll function just like we showed here. Okay, so just to add a few slides, I'm going to touch briefly on troubleshooting problems with divergence. It may occur that when you try to run power flow, you get an error that says the solution is diverging, or it's not converging, or it's stuck, or whatever. So some things to think about. If it's failing right off the bat as soon as you build the model, most likely you have something incorrect in the model. And the things that the program will hiccup on are if you put the generator rating in kVA instead of MVA or vice versa. Same with the transformer. Also, if you have the incorrect voltages, primary and secondary voltages reversed on the transformer, that can create problems in power flow, as well as other things, but certainly in power flow. Voltages entered in volts instead of kV, that's a real common problem when people are just getting started with EasyPower. All the voltages must be entered in kV. So you want to check those things. If you have a big model, if you want to track those down, if you just start deactivating parts of your system until you get the power flow to run, then you can kind of narrow down gradually where the problems are. Okay. Now, other things that can cause problems, we talked about those VAR limits in the generator when you're in PV mode. So if you have those set too low, that can cause a problem. The load tap changers, that can be a problem. If you have load tap changers and you're getting divergence, I would suggest you turn off the LTC or block them. Sometimes that'll solve the problem. You can double click on the breakers to open them and reduce the load. And again, you can just deactivate to see if you can find out what part of the system is causing the problem. And once you get it to converge and get a solution, you can kind of start making very small changes in voltage and load to try to back into the system what you're trying to model. And there's some changes you can make in the number of iterations. If you see if it's reached its maximum iterations, you can increase those. You can increase the allowable mismatch, but in my experience, that's usually not going to help once it fails. Look at the summary report and the mismatch report. That can help you kind of narrow things down a little bit. It's important to change really only one thing at a time so you can keep track of what's going on. But lastly, you get free tech support from us. So if you have a problem that you can't resolve with power flow, just send us your file, tell us what the problem is, and we'll take a look at it and try to help you out, because it can be a little frustrating sometimes when you can't get the power flow to converge. Okay, so I got quite a few questions people have sent in here. So let me see if I can get through these, if you guys want to stick around. And if not, it's 11 o'clock, so thanks for joining us. And I'm not exactly sure when the next webinar is going to be, but we'll be sending out emails on that. So first question is, I missed part 1 of this webinar. It should be available on the website, I believe. I'm not exactly sure where it is on the website, but we'll let you know about that. But they should be recorded and should be made available on the website. Question, should the power flow model be created with the worst case power demand, or should a demand factor be applied? So you want an actual real power flow case. You want the actual real world power flow or whatever you're trying to simulate. So the demand factor is not used in power flow. That's only used for the NEC sizing type calcs. So changing the demand factor will not have any effect on power flow in EasyPower. Question on the VAR limits for the PV inverter. Yeah, I'm sorry, we just kind of ran out of time, and I was intending to cover that this session, but we'll have to forego that. If you have a specific question on that, you could shoot an email to tech support, and we'll be glad to get back to you on that. What is the difference between deactivate and open the breaker? Effectively, it's going to accomplish the same thing depending on which breaker you open, but it's kind of two ways to accomplish the same thing. It's a little easier graphically if you deactivate something and you know that's out of your system. You can also run into problems with isolated systems if you just go around opening breakers. So it's kind of 6-1, half the dozen the other, whichever one you want to do. Excuse me. Question on, so don't most cogen models generate enough power and use import-export kVA to control load on the generator? Not quite sure I understand the question. Most people with cogen systems want to produce as much kW as possible. They don't want the kW to change because that's how they make their money. They want the utility to make up the difference. The utility doesn't necessarily like that, but if you are a merchant plant or you're a cogen facility, you basically want to run maximum kW all the time, if you're assuming you're getting paid for export. So if you're not getting paid for export, you're only offsetting what you buy, then yeah, you might have to have a different model there for how you regulate your kW. Also, the turbine generators generally like to run at a constant power. They don't like swinging back and forth in load. Question on wind turbines. How do you model wind generators providing power to the utility? Those are typically going to be like a PV source. It depends on the type of generator. If these are like the type 4, they're full inverters, and you're going to model that basically, it's going to look like an inverter to the system. So you need to model it that way. If it's an induction machine with some kind of power factor control, you're going to want to model it as an induction generator. So it's kind of a special case, but they can be modeled depending on the type of wind turbine. There's quite a few different options there. How do you determine the control angle for multiple utilities? Well, as we already said, that is some information you would have to get from actual knowledge of how the system is configured and the state that it's in, or it's kind of the what if thing you're playing to try to recreate some existing conditions. All right, so question, I have seen voltage controllers used to control power factor on motors by reducing voltage. Yeah, so it's going to depend a little bit on the type of motor. There was kind of a fad a few years ago. People were claiming to save energy by reducing the voltage. That's really only going to be the case for extremely lightly loaded motors because you can reduce the reactive power. But a motor needs to put out 10 kW, it's going to have to put out 10 kW, and that power has to come from somewhere. So reducing the voltage is not going to change that. So it's a very limited capability, and that only really works for very lightly loaded motors. When modeling a step voltage regulator, voltage is 1-to-1, but since it is 3 wires in and 3 wires out, do you model it as a YY? Yeah, typically for the step type, I would model it as YY. That's how it's actually going to be connected. So yeah, that's YY. Why do you have 2 scaling factors at MCC and panel? Not sure I know what you're referring to. When we do the group scaling, it's broken down by the type of equipment, whether it's a motor, generic load, MCC, or panel. So within that selection area, you can scale all the MCCs, all the panels, all the motors, but they're broken down by groups. So in that example we did. We have a transformer that only supplies power to a single motor. Can we use LTC to fix the motor starting voltage? Probably no, because the LTC is too slow. So it takes a fixed amount of time for it to change taps and respond to the low voltage conditions. So it's going to be too slow. And that's not going to help you at all for motor starting. One thing you could do is manually raise the voltage before you start the motor. And that would be kind of a nuisance. So in general, the automatic LTC is not really going to help you for motor starting. All right, so any other questions? All right, well, sorry we ran a bit over. If you guys have specific questions about what we talked about here, you can email me. My email address is david@easypower.com. Just david@easypower.com, and I'll be glad to get back to you. All right, so I appreciate everybody joining in today, and hopefully you got something out of it. And anyway, thanks for joining us, and hope you have a good rest of your day. Thanks.